Today, we're tackling a problem where you need to sort an array based on the relative order of elements found in a second array. The twist: any elements not present in the second array must be appended in ascending order. How would you approach this efficiently? You're given two arrays, R1 and R2. All elements in R2 are distinct and also present in R1. Your task is to sort R1 such that the relative order of elements matches R2. Elements in R1 that are not in R2 should be placed at the end of R1, sorted in ascending order. The core challenge is maintaining this specific relative order while handling the remaining elements correctly. A straightforward but inefficient approach would be to iterate through each element of R2. For each element, we'd scan R1 to find all its occurrences, add them to our result, and mark them as used. After processing all of R2, we'd collect the unmarked elements from R1, sort them, and append them. This involves nested loops for finding elements, making it quite slow. The repeated scanning makes this O, n times m for the first part, plus big O of n log n, logarithmic time for sorting the remainder, leading to a total time complexity of around O, n times m plus n log n. Space complexity would be big O of n for the result and a Boolean array. The key insight here is that the numbers in R1 are constrained to a small range, typically up to 1,000. This hints at a counting sort approach. We can declare a frequency array, let's call it count, sized to accommodate the maximum possible value plus 1. We iterate through R1 once to populate this count array, storing the frequency of each number. Then we build our result array. We iterate through R2. For each number in R2, we append it to our result as many times as its frequency indicates in our count array, decrementing its count each time. Finally, after all elements from R2 are placed, we iterate through our count array from 0 up to the maximum possible value. For any number that still has a positive count, we append it to our result array until its count becomes 0. This ensures the remaining elements are added in ascending order. Let's trace with an example. Suppose R1 is 231324 and R2 is 214. First, we populate our frequency array. Count will show 1122s, 23s, 14. Now we build our result. We process R2 first 2. Count for 2 is 2, so we add 2 2s to our result 2 2. Count for 2 becomes 0. Next, 1 from R2. Count for 1 is 1, so we add 1 1 2 2 1. Count for 1 becomes 0. Next, 4 from R2. Count for 4 is 1, so we add 1 4 2 2 1 4. Count for 4 becomes 0. Now R2 is exhausted. We scan our count array from 0. Only 3 has a non-zero count of 2, so we add 2 3s to our result, 2 2 1 4 3 3. Our final sorted array is 2 2 1 4 3 3. This is correct because the elements 2, 1, and 4 maintain their relative order from R2, and the remaining 3s are appended in their natural ascending order. You'll spot this pattern when you need to sort elements with a custom order, especially when the element values are within a relatively small, positive range. Look for problems involving frequencies, or when a simple comparison sort would be too slow due to specific ordering constraints. Time complexity is O, n plus MaxVal, where n is the length of R1 and MaxVal is the maximum possible value. Space complexity is O, MaxVal for the frequency array. This counting sort technique is powerful for specific sorting challenges. Try the next problem to solidify this pattern. Don't forget to like and subscribe for more DSA insights.